Hey Vivek, go and clap once again. Call people. Okay. So today we will briefly review statistical physics, formulation of statistical physics, and if I get time, then the concept of and the idea of phase transition. Okay, so in the last two lectures we have uh, uh, discussed thermodynamics, which mainly deals with how to describe macroscopic properties of macroscopic systems. But in 20th century, the one of the main achievement is to realize that that matter is composed of many elementary constituents like atoms, molecules, spins, and also to figure out the dynamics of these elementary constituents. And since we know that, then it's natural to ask that if the matter is composed of those things and if we know the dynamics, how to get the macroscopic description that we do in thermodynamics from a microscopic point of view. And that's what is attempted to do in statistical physics, okay, mechanics. So what it does is basically trying to, it provides a, the formulation provides a probabilistic description to understand and the macroscopic properties of equilibrium system. Okay. Now we have already understood what are macroscopic properties, the equilibrium, macroscopic equilibrium in macroscopic systems. I now will try to understand what does this mean, probabilistic description mean, right? So this is what we want to do. So and that we want to do it starting from a microscopic description of the system, okay? So for that, let us um, uh, try to look at, no, okay, before that, did I want to say something? Yeah, okay, so why do we want to do a probabilistic description? So that's a difficult question, and we do not have much time to discuss that. But the thing is, at least you can say that even if you are, so macroscopic means that you have like trillions of trillions particles, and they have these degrees of freedom. And even if you know the degrees of dynamics, first of all, even if you know the dynamics, will you be able to solve? And if you are able to solve, will you be able to use it to get this macroscopic behavior? So it's a formidable task. Second, for all practical purposes, you cannot do that, because those dynamics is so complicated that any tiniest perturbation actually makes it this thing that there is no point in solving those dynamics. So then the best thing that you can do, you can try to do a probabilistic description and expect that the means in that probabilistic description reproduce thermodynamic behavior. Okay, so that is what, with that expectation, we'll try to do try to give a probabilistic description on microscopic states. So probability on microscopic states. So what are microscopic states? So once again, we'll have our this prototype example of a gas of molecules. Okay, so what is a microscopic microstate? So there are n, let's say n particles. Okay, and a state, microstate of this system is to specify the positions and the momenta of all the particles. Okay, I'm just considering one dimension, but you can think of them as vectors also. Okay, if they are of they have spins, then you just specify their spins. If they are dipole moments, then you just specify their dipole moments, right? Do I have any more examples? No. Okay. So these are microstates, and they live in some space. We call it gamma, and that will be specified by the macroscopic constraints that you put. For example, the energy of the system, volume of the system, or is the number. I goes from 1 to something, right? So n also restricts this space. So this will be restricted by the constraints that you have put on macroscopic scale. Okay. So for example, for a system of n particles with energy E in volume V, so this will be represented by all such states which satisfy, let's say there is a Hamiltonian which is equal to E, and the fact that all the mu's are within V, let's say, of space V, and the total number is n. Okay. Okay, I goes from 1 to n, or maybe I'd say I into 1 n. Okay. So this is the space in which you have these microscopic states. Okay. Now, however, we are interested in macroscopic description. So what kind of macroscopic description that I can think of? We have done thermodynamics, so you know what kind of macroscopic properties that we are talking about. So let's say we have this gas. One easy description would be like, let's say you divide the box into parts and say what is the number of molecules this side and that side, right? Kunal, okay. So this is one description, but you can have you can make it a bit more refined description, which is like you can divide the box into, let's say, let me draw a bit more realistic box. Okay, and let's say you inside this thing you draw a small box of volume V, and this is capital V, and you ask what is the number of molecules in this volume V, which is centered around some position X. Okay, right, and then all possible positions, and it can give you a description of this. Or you can also divide by V, and then it gives you a density. So density function, right? Similarly, you can also think of magnetization density function. See if I have more examples. Yeah, maybe formally you can define this in Vx to be sum over all particles positions such that the particles positions are within volume V. This is an indicator function that says that this is within volume V centered around X. Okay. Okay, so this, if Xi is within this, then it is 1, otherwise it is 0. Okay, and you can divide by V and make it rho. Similarly, you can define momenta as 1 over V momentum density, Pi, this thing also. These are kind of a bit more formal way of defining this kind of macroscopic quantities. Okay. Similarly, magnetization, and we want to understand these properties of this. Okay, but question is how. So the expectation is that we want to describe. So in general, we can think of these observables, these macroscopic observables are basically functions of the microscopic configuration. Given a microscopic configuration, I can determine this quantities, right? So these are observables, functions of microscopic configuration. Given a configuration, I can do this. Then I say that the values that we want to reproduce in thermodynamics, that suppose we get this value for this observable, should be equal to this in this probability description with respect to some average, okay, over the microscopic states. So this is one thing. I will not let us say that, okay, we just want the discussion to be like this. Okay, let's not go into the discussion of why we should do this. That will require other further discussion. And second thing that we want, what distribution that we want, so that this could be true. Okay, is this clear? Okay, so then there is a hypothesis which says that for an isolated system of energy E with volume V and N, this P of mu, of course this should be characterized by this macroscopic description, is equal over all the microstates probability of occurring is equal, which means that it has to be the inversely proportional to the volume of the space, which is E V N, right? I can write it a bit more formally, so I can just say that this is P of mu. Let's not write this thing once again every time. So it's actually 1 if H of mu is within this gamma and 0 otherwise. Proportional to this. Okay. So this is called equal a priori probability hypothesis. Okay, so this is what we assume, and it works. So for the time being, let's just say that, okay, this is what it is, and we just proceed. Okay. Actually, for practical purposes, the system's energy cannot be specified with an accuracy, these things. So usually one puts that, sorry, I said I made something wrong. This is equal to E. Okay. And also other constant that the volume, these things would be within the volume and the number is in these things. Okay, so usually you do not have energy specified accurately. You can specify energy with some error, plus minus delta by 2. Okay, then you just define this probability that this mu is 1 over sigma. So basically what you do is basically you take this energy surface, now let's say this is the surface, energy surface, and this is the volume of this energy surface, and you take a delta by 2 region around this and take this volume, and that we call it omega delta E, just to make it a bit more precise. And this is equal to E1 if H mu is within E minus delta by 2 to E plus delta by 2 and 0 otherwise. Okay, good. So now I said that, okay, I have given you a probability distribution, and then once I have given you this thing, you can compute this quantity. Now whatever you compute, that you should say that we should connect it to the things that you that you can observe in a thermodynamic process or thermodynamic system. So I would like to make sure that. So how do I make a connection between this? So that connection comes. So making that connection is done by identifying one quantity, which is entropy. Okay, if we can identify the entropy of all these states specified by these macroscopic variables, okay, all the microstates entropy, then if I can identify, then I can actually do all the thermodynamics, all the quantities I can derive, right? Because that's what we did. If you are given the entropy, then you can compute all other things. So that's why the Boltzmann's genius comes. He said that let us define this quantity SB. For the timing, I am calling it SB. It's called the Boltzmann entropy. Boltzmann defined this quantity. I am calling it as Boltzmann entropy. Is log of this volume. Okay. He says that, okay, let us define this quantity. This is also a function of EVN. Remember, in thermodynamic entropy, the Clausius entropy was also a function of EVN. Okay, and from this we could get all the relations, like what is the temperature, pressure, and all these things from the derivatives of this function. Question is whether does this function also has all these properties? Can it describe first law, second law, all these properties? And Boltzmann showed that yes, it can. And then one can think of this as a legitimate candidate for this. Okay, so this is the connection. So this is equal in the thermodynamic limit. Okay, so any question till now? Okay, so let's see how this quantity can reproduce or at least describe all the features of thermodynamics. Let us see what are the things that we. Okay, so in between there are a lot of other discussions that I skipped through, but if you are interested, for example, why this kind of distribution and why you what is the justification of doing these things, so we will not go into that details. Okay. Second, okay, let's not go in there. Okay, so we want to understand the properties of this thing, whether this can actually describe all the thermal equilibriums, first law, second law, this. Okay, so let's see. For that thing, once again, we'll consider an example scenario, which is, let's say, our favorite simple system of system, and consider two parts of the system. Okay, E1, V1. Let's say E01, V1, N1, E02, V2, N2. Okay, and let's say this was divided by some barrier, and now we change the properties of the barrier so that they can exchange energy. And we ask what would be the energies between these two parts. Earlier, what we had asked that what is the energy. Now we'll ask what is the probability. So this energy, so the total energy is E total is E01 plus E02 is constant, because this full system is isolated. Now once we change the properties of the barrier, these energies can get divided into many different ways. And previously in thermodynamics we had asked what is the energy division, particular energy division at which the entropy, the thermodynamic entropy was maximum, right? But now we will not ask that. I will ask We'll ask what is the probability of this. Of course, this E2 is just E total minus E. So just we can ask what is the probability of E1. Okay. Now we'll ask that. Okay. Given that the probability of the microstate of the full system is this. Is the statement and the problem clear? Okay, good. So let us try to ask, can somebody tell me what is the probability? What could be the probability? Let's say this is the volume, omega. I have changed the notation, but gamma and omega, after I put delta, I will say there is some delta, but we don't need this anyway. So let's say this is the volume for the full system with this energy. If this is given, huh? Okay, but in any case, how would you do that? Let's say this is the microstate. This is the microstate of both the parts. Okay. Formally, how would you write? So these two parts means that there is a Hamiltonian which we can write it as H part 1 plus H part 2. Right? Yeah, how?
Given the total energy
How?
multiplied with the probability that the total energy is each is 1 by. We can use the delta.
Yeah. Okay. So basically, if you can put these delta functions that H1 mu is equal to E1 and H, that thing is anyway automatically satisfied. So, but you need that condition times the probability of mu of the total system. And if you do that, you will see that this will be omega of the system, first system, that it is E1, V1, A11, and the second system is E2, V2, N2. E2 is E minus E2, E1, divided by total. And that total you can still write as this thing, right? E1 let's call E prime. Right? That is the probability of, it's clear, right? So this is the probability. So let's see what is P of E1 is. I can write down this quantity by this definition, exponential of, and there is some constant, exponential of S1 by Kb plus S2 by Kb. I'm just writing S1 and S2 as by, for this factor S1, for this factor S2. Okay? And this is E1 and this is E minus E1. Maybe I should write, let me write it. And S1, S2 are same function, they just, so I don't need this extra label, okay? Because I have said that these two are same system, like both sides you have oxygen, let's say. Okay, good. Now, how does this probability look like? Yes. So let's say this is the E1, E2 plane, and this is the line which says that E1 plus E2 is constant, which is E. E1 plus E2 is E. And let's say this is the partition that we started with. This is E01, this is E02. Okay? And then we made the wall conducting, and they just do all the energy exchanges, and then they go somewhere. From thermodynamics we know that it should go this E1 star, E2 star. I mean, that's what we expect. So that means this probability, if we want that the energy of the first system to be this, and automatically this, that means average energy of the first system to be this, then this probability should be highly peaked around this, right? So I want this function to look like this. Like this. It's extremely peaked around this point, around E1 star, right? So let's say if it is that, then we at least, by this description, we can at least try to figure out, reproduce that the mean of this distribution is coinciding with the thermodynamic value that he would compute. Okay. Now, what about the fluctuation? Okay, before that, let's try to find out what is E1 star. So as I said that the E1 star is the position at which this distribution has maximum. So if we try to find out what is the maximum, that means you have to maximize this exponential, right? So we try to maximize. If we maximize, this calculation is exactly same as the entropy maximization problem that we did in thermodynamics. Now here all these S's for the time being are this SB function. I'm not writing this B, but this SB. Okay. So that means this maximum says that del S, del E1 star is equal to del S, del E2 star at E2 star. So this says that and that is a condition for equilibrium. I can think of this as a condition for equilibrium, right? Okay. And then once again I can reproduce this identification of temperature. The system temperature of this left part is equal to temperature of the right part, and I can call it temperature. So that means I can get a definition of the temperature like this, right? Even though this is Boltzmann entropy, this function, but I get a similar expression. So at least this function shows the same property as this function shows. Similarly, you can do the same thing, make the wall moving and then do the volume changes and the full calculation you can do. But this description not only says that the mean value is with this, it can also describe the fluctuation in equilibrium. That's an extra thing that you can get from this. So what about the fluctuation? Okay. So that means how peaked the distribution is around this E1 star. So let us try to see that. So if we want to find out what is so we know that this function is peaked around this. So let us expand that exponent, the exponent. If we expand that exponent, is some constant, and then you have S of E1 star plus S of E2 star divided by KB plus, let's say I want to expand around E1 equal to E1 star plus delta E1. So what is E2? E2 is E1 minus E minus E1 star minus delta E1. So delta E2 is minus delta E1, right? So then I'll have half del 2 S del E2 E1 star minus, let me see, what did I do it? I want to just write, oh yeah, I can just write this plus del 2S del E2. Right? This is E minus E1 star. Okay, but since this quantity is maximum at this, the linear order terms are not there, and these are negative. Okay. Okay, so this should be equal to, let's say I just call it minus C. Okay. So then this probability of E1 is some constant times exponential minus C by 2 delta E square. And C is proportional to del 2S del E square. Now let's see what is del 2S del E square. So what is del 2S del E square? Del 2S del E square okay. We'll try to compute this thing. It actually is related to the specificate, but we'll compute that. But before that, let us try to compute what is delta E square average. Delta E is basically E minus E average. So delta E square average will be some constant by C because of this. Now let us compute this, the relative error by E star, E1 star, is this by E1 star square root C, right? Is this clear? Now let us compute this quantity E1 star square root C, but let's call E1 square and C. Let us try to compute this. And if you compute, so basically E1 square and del 2S del E1 star square. This you can show del S del E is temperature. So del E1 star 1 over temperature. One can show that this, I mean, you just use all the relations. And let's say you define an energy per particle is E by N. I'm not going into the details of this calculation. Finally, you can show that this can be written as E square by T square del E del T inverse. Okay? You just do this calculation. It's and the temperature, and this thing is the specificate inverse, CV inverse, specificate per particle. Okay? Good. Why did I want to do that? So that means the relative fluctuation in E is actually minus N square root of that, of course. So N times E square by T square 1 over CV square root. Okay. So now this quantity is 1 over that. So this will be 1 over this quantity. Okay, 1 over this quantity. So this in the n going to infinite limit, this quantity is very, very small. But in this thing, I have assumed that this thing is finite. The CV is finite. But this CV may not be finite. There could be situations in which this CV may not be finite. You know where? Yes. And there, this calculation will not hold. And Consequently, the fluctuations cannot be described by this. And that's why you have large fluctuations in phase transitions, and there you have to do these things differently. So just to make that remark, I did all this calculation. Okay, good. So temperature you can get, and the fluctuations also you can characterize. Similarly, you can also do the same calculation if you do, instead of doing energy, suppose you change the volume, okay, so that the system can only, this wall can move, but no particle transfer, no energy transfer, let's say. And in that case also you can do. And similarly, if you allow both energy and work, all this you can do the similar calculation. What you get is the following. You see that finally the peak of this distribution, where the entropy is maximized. Suppose I have identified that, and let's say where this is maximized, the exponent is maximized. Let's say that is E1 star, V1 star, and N whatever. Now suppose you change the volume at that position from V1 star to dV1, let's say. Then what is the change in the entropy? The change in the entropy will be S of E1 minus P dV, because that is the amount of work you perform, and let's say V minus dV, and N minus S of Vn. And you can do this calculation and you can show that you get del S del E into P plus del S del V, the whole thing into this dV. Now since we are doing these changes at the maximum, where the S is already maximum, this change should be 0, right? Which means that del S del V is minus P by this quantity, del S del E, which is temperature, we have already identified. So we get this relation. Now suppose we do both the energy and volume, both changes. So there is a change in energy, there will be minus dE also. Okay, suppose you do that, then you can find out that the change in this thing, do the similar calculation, you will find that you will get dE by T, because here you will get P dV and also dE. So you will get dE by T plus P dV by T. And if you rearrange this, you see that I can write down the change in entropy in equilibrium as TdS minus P dV. And this, you see that the changes in equilibrium. So I am in equilibrium and I want to change the equilibrium from this thing by little bit amount. Suppose from this equilibrium to another equilibrium which is slightly different, what is the change in this equilibrium entropy? That I have calculated, and that says that it is related to the change in the energy by this, and this should be the first law, and it is in the form of first law. So this entropy can actually describe first law also. Okay, now let us see, we have already seen by drawing that, I should not have erased that plot. By drawing the distribution, we have already seen that this distribution automatically, by demanding that the distribution has a maximum at E1 star, E2 star, by demanding that we have already satisfied second law. Which means, I have to draw once again. So initially it was this, E0, E01, E02, and finally it goes there. And we know that the probability distribution is like this. So then definitely the product of this omega, this thing at 01, 02 is much smaller than this product here. Otherwise it will not have a peak here, right? So which already says that this also satisfies the second law, that the entropy is larger in the equilibrium state than any other state. Okay, good. Now let me briefly talk about a system connected to reservoirs and how do we describe such system. So here I have considered a similar system, two parts, they are of same size. Now let us consider a system which is connected to reservoir, which is at some temperature T, and you have a small system which is also large. But you can still think of doing some processes in this, but anything that you do will not change anything of this system. This is reservoir. Any changes that you make will not part of this system. It's always or any perturbation will die out very, very quickly. And it's all you can think of that this system is always in equilibrium at temperature. This thing. Now, what is so we use the idea of the isolated system probability distribution. By the way, I forgot to mention the distribution that I wrote earlier. It's called, you can think of that as describing an ensemble of systems, because once I give a probability, that probability can be interpreted as things which are distributed in some ensemble of systems. So that ensemble is called microcanonical ensemble. Okay. Now, in this case also we can use that. So let's say probability that the system and the reservoir, what is the probability? If I use the same idea, so it should be a system plus reservoir in total energy, and it is 1 for the total H system and H reservoir plus H reservoir is E total or 0 otherwise. So from this you ask what is the probability that the system is in, this is the joint probability, this is joint probability that the system is in this microstate and reservoir in this microstate. We ask what is the probability that the system in this microstate. Okay. So how do we do that? So this means that you say that you just integrate over all reservoir microscopic degrees of freedom, saying that the probability, once you do that, you'll get 1 over sigma S plus R E total, and let's say delta of, so the reservoir will have the thing that the delta of this thing. So this is in this, so that means the energy of the system is H of mu, or let's say, let me call it mu prime, and let me integrate. So energy of the system is mu S prime, let's call it E prime. Okay, so H of mu S plus H of mu R is E total, and the delta of H of mu S prime is E S prime. Sorry, mu S is E S prime. Okay, and you integrate over all the full this thing. What you will get is that you are integrating over the reservoir degrees of freedom with the condition that integrating over d mu r with the fact that the H of mu r is E total minus this E S prime. Okay, and E S prime is H mu S prime divided by this thing, which means that the reservoir entropy, reservoir, not entropy, the omega function at E total minus Es prime. That Es prime is h of mu s prime divided by sigma s plus r. Okay. So this I can again write is proportional to, or is some constant, e power s by kb E total reservoir, E total minus h mu s prime, right? So now what I can do is I want to expand this function. So then P of mu s is constant, and then if I expand around this, whatever constant I have, I absorb it, I get it there minus del SR by del E total by KB into H mu S, Hs mu S. Yeah, I should have put HR, but okay. Now this is, I know that this is the temperature of the reservoir. So the system is proportional to the minus Hs mu S divided by Kb Tr. Note that I have neglected the higher order terms. There are higher order terms in this expansion. Okay, and if you look at the higher order term, let me see what is the higher order term. So the higher order term will be del 2 SR del E square times delta H system square. First of all, H system is smaller, even though it's large, but it's much smaller than the reservoir. So this quantity is what? This quantity is actually 1 over, you can show that it is actually 1 over, proportional to 1 over T square over specific heat, not the specific heat per particle. And this quantity of the reservoir, and this quantity is very large. So that means you can actually neglect those higher order terms in the limit of infinite reservoir, and assume that the reservoir is good. The reservoir is not at a phase transition point. Okay, so you can do that. You can always assume that. Okay, so then the distribution of a system which is connected to a reservoir, the probability that the system will be found in a particular state is e power probability that this is e power minus is called beta. This beta is the same temperature of the reservoir. So beta H mu s divided by the normalization, and beta is 1 over kBt. So since we can now forget about this existence of this in the mathematical formulation, and just write that this is it is in contact with the reservoir at temperature T. Now what is Z? Z is the normalization. This is mu s e power minus beta H of mu s. Okay. Now ask what is the probability that the system is at energy E. Can somebody tell me what is this? Huh? What this? No, it cannot that. Huh? What is this? What should be this? If this is given, what is this? So let's compute. So what do you want to do? You basically want to sum over all microstates with the fact that the system this thing is E and P of microstates, right? So then this is 1 over Z, sum over mu s, delta of H is mu s minus E, and this thing is e to the power minus beta E comes out. Okay? Now what is this? This you have done already. This is the microcanonical calculation, right? This is the number of states with energy E. So that's the omega. E by Z, this is the omega of E. Right? So probability of E is different from, so usually they are given with the same notation in the textbooks and people get confused. This is this and these are different. Okay? This is a pure microscopic description. This is a slightly coarse-grained description. You want the system is in energy E, but with system can have energy E in different microscopic states, and that is the degeneracy. You have to multiply. So this is equal to e power minus beta E, and that thing I can write down as S by Kb, okay, and by Z, and I want to write it as 1 over Z e power minus E by, what is it? E minus Ts by Kbt, right? And then we have seen such a quantity, we call it F. Till here, S is also Boltzmann entropy. But I have seen that, I have shown that Boltzmann entropy has all the properties of thermodynamic entropy. So for the time, from now, we'll just consider this as the entropy of the system. F of E divided by Kbt. Okay? So let's write what is Z. So Z is this, but I can still again write it as integral over sum over E and then omega E to the power minus beta E, right? I can write it that way also. I am just grouping over the microscopic configurations which have energy E and then sum over all those groups. That's what I am just doing. So Z can also be written as sum over E to the power minus basically beta F E, right? And this is, so that means e to the power minus beta F E divided by sum over E to the power minus beta F E. Okay? Now for a system which is very large, thermodynamic system, this quantity of free energy is extensive, so then you should write this quantity by saddle point calculation. You should do that. So what is the saddle point calculation? In this summation will be dominated by that value of E in which this is minimum. So this is, I am just writing it down as beta F E star, where E star is that, E star is determined by this thing where it's argmax. Okay. So if it is that, then I can write it is e to the minus beta F E minus F E star. So the probability that the system, what is the probability that the system will be found in E star is actually the largest. What is the probability that system will be found? So that is the equilibrium, right? Because this is the minimum at which it is, that is the equilibrium free energy. And what is the probability that you will find the system at some other energy? What is the probability cost? That probability cost is exponential minus beta of this thing. This thing is positive because if this is minimum, this is positive. So the probability of finding the system at some other energy different from E star is exponentially small in the change in the free energy. Okay? Okay, good. Now, actually I am skipping many things, that's why I have to see what I want to say. But there is another relation that I have to, so from this at least we can see, from this thing I can see that the free energy in equilibrium of the system is actually minus kBt log Z, right? Right? But you can also make some identification from other ways also. So let's say, how do we find out what is the average energy? This identification, I did this identification from this, but you can also do it from other known thermodynamic relations. So let's say, what is the energy? Energy of the system. Where is the energy? Average energy of the system. So, 1 second. One second. So we know that the energy, if we can compute the average energy, suppose if we compute the average energy from this relation or whatever, from this relation, what do you get? You will get that this is minus del del beta of log of z, right? I think it is that. Is it correct, right? It should be correct. On the other hand, you know the free energy is E minus Ts, and T, you can show that using, you can write it using this Legendre transformation, E equal to F plus Ts. So F and S, you can write the Legendre transformation that I have told you yesterday. Now you have to do this for functions between F and E. I did it for S and E. Now you can do it for F and E. So you see that this is this. S can be written as minus del F del T. Sorry, del F del T. It should be minus sign. Okay. Now this you can write it as del of beta F by del beta, where beta is 1 over T. Okay. This you can just, this relation you can write it in this form. And you can see that if you relate this and this, you can also say that beta F is minus log Z, which also says that F is equal to minus KB T log Z. Now, what did I do? I just said the same thing, exactly the same thing, whatever I have done here, in a bit more complicated way, because you see that the Legendre transform that you do here is actually whatever you do in a saddle point calculation. And the saddle point calculation, what you do, you basically find out the maximum position. And that's what I did. So it's just the restatement of that thing. Okay, good. And once again, once you have given, then you can also find out what is the fluctuation, E minus E average, whole square, all this thing, you can compute. So I do not want to go into that. Okay, because it's very difficult to do starting from this micromechanical and go to phase transition. So I have to skip many things. So okay, so let's let me give you one example which you can do, and just, if you have forgotten, just do this example, you'll remember everything. So let us consider that we have n two-level systems. We can think of them as spins. So we have either, let's say, 0 and epsilon, let's say. So the energy of the system is E Ni equal to 1 to n, and Ni would be 0 and 1. Okay, so these are like microstates of the system. Okay, and energy, it's like Hamiltonian is expressed in terms of the microstate. Okay, and you can ask what is the probability. I mean, let's say it's in its thermal equilibrium at temperature this, Then the probability of this thing is 1 over z e to the power minus beta sum over I ni, and you can ask what is the energy of the probability that the system has some energy E. You can find out partition function T n, you can find out. And you can also ask what is the probability of finding one spin, this is called the single point distribution, in state, let's say n. You can ask that. Okay. You can, this is what I did it, assuming that this is in equilibrium at temperature T, but you can also ask the same thing, saying that this full system has some energy E, microcanonical, and ask this question. Okay. So another part is consider isolated version of this, where the total energy of the spins in spins is E naught, let's say. So E naught is equal to I equal to 1 to n epsilon ni. Find out what is sigma E naught n. Also compute what is the probability, single point probability, what is the probability of finding one spin n. And you will see that whatever you get here, you will also get same thing, you just have to identify the temperature properly. Okay, so that's another thing. Sorry? Huh? P1 is the probability of finding one spin in state n. N is either 0 or 1. What is the probability? Just find one. What is the probability that you find one spin? That's 10. Okay. Okay, another thing I want to quickly mention, maybe that is the most relevant for the course next week, is that all this business can also be obtained from just a simple entropy maximization principle. But for that thing, there exists another version of entropy, which is called inequilibrium. Actually, that version of entropy exists. It's called the Shannon entropy. Given a probability distribution over some state space, this is defined by this. Okay. I will not go into the discussion of why this is an entropy, how this has all the properties of entropy. I will not go into that. Just take that this is a definition. So given a probability distribution, this is an entropy which measures the amount of information in the system which is described by this distribution. Okay? And this also in equilibrium, if you use all the equilibrium distributions, whatever you get, this also gives you exactly the same quantity as Boltzmann entropy and has the same property as thermodynamic property. Okay, so now given this thing, I should, for example, if I said that this is 1 over gamma, right? So mu for microcanonical distribution, this is 1 over omega log of 1 over omega, and you see that it is actually, so you should put a kb here. Let's put kb. So you'll get kb log omega, right? You see that you automatically get this for a microcanonical ensemble. Any question? You have any question? Okay. So this is an example. So if you take p mu equal to 1 over gamma, 1 over omega, then you see that it gives you the Boltzmann entropy. Good. Now let's say how do I get the probability distribution of a canonical ensemble? By maximizing this entropy. So in the canonical ensemble, let's say energy is specified, average energy is specified. Average energy is specified because the temperature, given temperature means the average energy is specified. So suppose average energy is specified, what should be the distribution that maximizes this entropy? And I will show that we will get the canonical distribution. Okay. So let us maximize this entropy subject to this constraint. So let us maximize this function. What is it called? Some g. This is a functional of p mu. Okay. So what is this? Minus kb log p mu okay, because average energy formally you can write down this thing. There is some Hamiltonian function. I am just writing, instead of h I am just writing e and this thing. Okay. Given this I want to find out what is this that maximizes this. Right? That's the question. So that means that I have to find out del g del p mu equal to 0, and you see that this should give you kb log p mu log p mu plus 1 minus 1 right, minus kb. Let's absorb this kb into lambda, or let's put this thing e mu equal to 0. I made some mistake, there is a minus sign, right? So what do we get is p mu. Actually I think my kb is creating a problem, but let's see how far we can go. So p mu is some constant times e to the power minus lambda e mu, lambda by kb e mu, right? I think I made a mistake. What mistake did I make? Can you tell me? I forgot to put another constant. Normalization, right? I forgot to put another constant, but anyway, even if you put it, everything is here. Everything is in this constant. Okay, let's just put C. So now this C, you have two constants that you have to figure out. One is you can figure out by saying that d mu p mu is 1, which means that C is equal to 1 over integral d mu e to the power minus lambda by kb e mu, right? Second, so this is like partition function already. Second is that average energy, this thing is given, E is given, A is actually, you have to put it in this d mu, E mu, and this P mu, e to the power minus lambda by kb E mu divided by that integral. Okay, and this is actually, if you think of this as beta, so this call this thing beta. So then this will be minus del beta of log of z, and call this thing as z beta, log of z beta. Okay, so you have some function of beta equal to E, just solve for that. So beta as a function of E you can solve, and then this whole distribution will be specified. And finally what you will get is, so basically solve beta as function of E, average E. So finally the solution that you get P mu is e power minus beta E mu divided by integral d mu to the minus beta E mu. That is exactly the canonical distribution that that I wrote from the other description. So what I am trying to say is that all this distribution, then you can actually relax other conditions also, let's say volume and other. All this distribution you can get by maximizing this. You just have to put other conditions. So and for each condition, you just have to put different Lagrange multipliers, and all these Lagrange multipliers will give you a set of equations. So if you have 3 Lagrange multipliers, you'll get 3 equations plus 1 from the normalizations. So you have four constants, 4 equations. You just solve, and then you'll get this. Always you'll get a form like this. Another remark is that all the formulation that I have done, you can also extend to quantum systems, and of course the states will now be in Hilbert space, and the energies will be in operator, and then the distributions, those things will be described by density matrices, and then this formulation you have to just extend there. Okay, good. Now let me talk about last 30 minutes on phase transition. So this formulation I have done and the examples that I have told you, you have to find out. So if you can find out the partition function, then yes.
Can we say that the loss of information is a consequence of maximization of the Shannon entropy?
What, loss of?
Information. The information loss.
Why do you want to say that? I mean, what is the relevance of the?
Is it true or no?
It could be, but I don't see the connection with the what I am discussing. It could be.
Entropy is related to information loss, right? So is it that if we maximize Shannon entropy, we get a loss of information?
No, if these informations are given, that average energy is given, and this thing, let's say this information is given, what is the minimum information that we have? That is what we want. Suppose if you are not given this thing, the amount of information is this. I mean, I should not say information. Actually, it's the amount of, how do I say, amount of memory that is required to put that information is this. Amount of memory that is required. So if you do not have enough information, you need a lot of memory to take the state. That's in that sense. So it has a lot of entropy in that sense. Now if you have little this thing, information, then that thing will change the distribution and maybe reduce the amount of memory required to do this. So it will reduce the entropy a little bit. Maybe I said completely opposite, but you have to change the sign. But yeah, I do not want to say, maybe in the next week the lecturer will probably say that thing. But I just wanted to say that if you define a function like this and do a entropy maximization problem that we have discussed in the previous 2 lectures, that finding the equilibrium state can be obtained by maximizing entropy given the constraint. If I do that, this entropy maximization principle is consistent with the distributions that we get from the other formulation. That is what I wanted to say. Okay. Now I said you can see that if you can compute the partition function, then then you can actually basically compute the free energy, and once you have the free energy, either the partition function or the entropy or the omega function, if you can compute those, then you can find out all the quantities, equation of state and everything, because that is the quantity that you start with. If you can do this thing, either free energy or the entropy, then you can do all the thermodynamics, all the derivatives, and you can take all these things. But the question is, computing that is very difficult. Second, for non-interacting systems you can compute, but for interacting systems, let's say if you have, for the time being, let's say I did not give you the example, but for let's say non-interacting gas, ideal gas, you can compute this, and you can reproduce all the ideal gas laws, the equation of state and everything. But now suppose if you put some interaction, then performing, so basically what is Z? Z is basically, let me write down just to explain the complexity. For an n particle problem in, let's say, in one dimension, you have these integrals. The minus sum over pi square by 2m beta, and then you have, let's say, beta of let's say these particles are in some potential xi, and they are interacting with some interaction, let's say this, and then there is also dp1 to dpn. So you have to perform this multi-particle multivariable integral. P part usually you can do, because usually you consider Hamiltonians of the form that you have a kinetic part plus potential energy part. But this, if you do not have this, then you can easily compute, because it's just the product of the single variable integrals. But if you have this, then it's very difficult to compute. Then there are some approximate methods. These are called virial expansions and all. And if you do that, there's virial expansion, some approximate methods. Then PV equal to NKBT gets changed slightly, and you get P minus A by V square. You get this G minus NB equal to NKBT, right? You get this equation. This equation gets changed. If Z gets changed, the equation of state will also get changed. You get Van der Waals equation. But this procedure of doing perturbation and doing this thing, doing adding terms order by order, breaks down at some point. Okay. So that's why you cannot do, and those usually breaks down at phase transitions. Okay. So why? Because the function itself starts behaving non-analytically, and where such expansions may not have, at those points the functions will not have expansions like this. Okay. And since the function z or the free energy shows non-analyticities, it means what? That its derivatives changes discontinuously as you tune a parameter, or maybe the first derivative or the second derivative, and those characterize phase transition points. Now, why do you think that there should be a phase transition? There can be a phase transition. Let me give you a brief argument, but it's not very rigorous. It's that basically the thing is, you have to minimize free energy. Let's say E minus Ts. So let's say at t equal to 0, you have to find out what is the state, macro state that you get. So at t equal to 0, you get the macro state, you just minimize the energy. And let's say at a very, very large temperature, infinite temperature, minimizing free energy is equivalent to maximizing entropy of the system. Now, the macro state that you get for the same system by minimizing energy or maximizing the entropy. Okay? These two macro states could be different. One could be gas, another could be solid, right? Right? So, and these two may not, this thing may not smoothly get connected by tuning a parameter temperature, these two macro states. So there could be a non-analytic points. Now the question is, how do you get non-analytic points in a Z? Z is like this, right? So each of these terms are analytic. Usually Hamiltonian is analytic for a system in a microstate. Each of these terms are analytic, but you have a summation of an infinite number of terms in the thermodynamic limit. So thermodynamic limit is very important for phase transition. For a finite system, this function cannot have any non-analyticity. A sequence do not have non-analyticity if all the terms of the sequence are analytic. Unless it becomes infinite, then it can show non-analyticities, right? So that's how it can produce non-analyticities, and then it can describe phase transitions. Okay, this is some general statements. Now let me give you descriptions of, just to remind you, from people have tried to describe phase transition from phenomenological point of view. Let me discuss this phenomenology for 5 minutes. So these, whatever I am doing, the purpose is just to remind you, not to kind of discuss or the phase transition in detail. So let's say the typical phase transition that we that we know or discuss is liquid gas. Let me just look at this way. Okay. So liquid gas phase transition, let's write it in this direction, P and V. Usually we write P and V this way. So if we do it this way, for your convenience, let me first draw P and V this way. So it's at very large temperature, these are isotherms. This is PV equal to KBT. This is at very, very large, T is very large. And then as you decrease, it starts becoming slightly different. And then, let me first draw a reference. Then it is this. Then you get a point at which you get a point of this thing, in which the derivative and the second derivative both goes to 0. So till this point, at some point here, the ideal gas equation describes these curves. In this regime, Van der Waals equation describes, but after this it cannot. And you get this relation, this kind of curves. And you see that this side is gas, vapor, and this side is liquid. And you see there is a region of V, where is liquid and gas both coexist. Liquid and vapor both coexist. Okay, at that. Okay. And you have this. So let me draw this thing in a rotated this way. It will be clear why. So this temperature is called a temperature, some critical temperature. Okay. So if you go below this temperature, you see this, and you see that liquid and vapor. So there is a phase transition. Okay. Before that, you had only vapor. That's called a critical temperature. So with temperature, there is a critical temperature. Similarly, with pressure also, with volume also, you can get this thing. So let me just draw them. You all know all these things. So I'm just drawing this thing is like this and then rotating. So it will be like this. And then you'll have like this. Then you have so this side is liquid, sorry, gas, and this side is liquid. Okay? Here. And this is TC. This is T very large. T large. Similarly, in PT plane, you have a line like this, which ends. There is a second order phase transition point, and this is a first order line. This side you have liquid, this side you have vapor. And if you look at in the BT plane, you will see that there is a region of coexistence. This side you have vapor, there is a TC, and you have two phases coexist. And we have liquid. This is for liquid gas transition. Let me give you the plots for the phase transition in a magnetic system, and then you will realize why I have drawn it in this way. So for a magnetic system, magnetization also changes discontinuously and undergoes phase transition. So let's say this is magnetization M versus H. Okay, so there is a critical temperature when T is very large. You see that the magnetization with H changes like this, and then there is at low temperature it changes like this. If you come from this way, then it is, and if you come from this way, it has this. So there is a discontinuous change. Now there is a critical temperature at which this behaves like this. Okay, so this is T greater than Tc, T equal to Tc, and this is T is less than Tc. You see, it is similar to this, that there is no discontinuity. This is like Tc curve, and below this thing there are discontinuities. Okay, and depending on t, how if you look at t even smaller than this, you'll get this curve like this. In the HT plane, this is similar to this. You have a TC. If you do, if at t less than TC, if you change H to H, this thing, you'll see a discontinuous change. But for t greater than TC, there is no discontinuous change, changes continuously. Okay. And MH plane, MT plane, which is like similar to V, you see that there is this thing curve like this. Here you'll have all up phases. Here you'll have all down phases, like magnetized up phase, magnetized down phase, and you'll have two phases coexisting. Okay, and this is TC. Okay. Okay, good. Now the thing is, these are the phase transition. How do you? So there is a phenomenology which tries to characterize the phase transition near the phase transition point, and it turns out that the behavior of these quantities, the equation of state, whatever you see, behavior and the response functions, which are susceptibility or the specific heat, near the phase transition points, shows some behaviors, power law type behaviors, characterized by some exponents, and it turns out that those exponents here and here are exactly same, and that's called the universality. So that calls for some theory of, some universal theory of phase transition which Landau had devised. I will not go into that, but let me briefly describe this phenomena. You can actually do it from a phase transition, from a mean field theory. Should I do that, or you all know? Should I remind you? But okay, let me remind that, and maybe while doing that I can make some remark. So let us consider, so just if you want to understand this thing, this behavior in a model system. So let us consider a model system, because it's very difficult to compute this partition. So similarly, you can write down the partition function for spins, where we will have interactions, and it's very difficult to compute that partition function for arbitrary interactions. So let us try to see some approximate method by which you can do. So let's say this is sigma I, sigma j. This is the nearest neighbor on some lattice where there is some this thing magnetic field, and sigma take plus minus 1. So I want to compute the partition function of this system. Let's say I just basically want to do z is equal to trace over e to the minus beta h. Okay, but it turns out it's very difficult to compute. This is in some arbitrary lattice in which each site has some coordination number z. Okay. Okay. So I want to compute that, but in order to compute, I use some ideas of this phenomenology. The fact that near in some phase, let's say in some ordered phase where you have some magnetization, I know that the system locally the spins are more or less ordered. Okay, and this ordered fluctuation happens over a large length scale. So if I assume that, then I can think of computing this partition function instead of performing integrals over microscopic degrees of freedom. Assume that I can actually perform integrals over these ordered states. Okay, so let's say these are sigma i's e power minus beta h, but let's say I'm doing one dimension. Let's say we have some magnetization curve like this, and instead of performing over this, let's say I perform over this magnetization m of x. Okay, and I can write down this thing h as some energy. So it should be basically, if you give this thing, it will be some free energy of given this thing. And how does this free energy come? Let's say it's beta E of mx, and then you have to perform over all the microscopic summation with the condition that whatever magnetization operator gives you locally this magnetization. Okay. Now this is same as this the entropy calculation. In the entropy calculation, what we did, we just summed over all the microscopic configurations given the energy. Here it's the same thing. You just I'm just summing over all microscopic configuration given a microscopic operator equal to a macroscopic value. So this will be some kind of entropy, and you have to find out that entropy, and then that entropy will go there. So it will be like omega, and you write it to the s, and this will make it f. Okay, and then you have to minimize this f, right? And then you have to find out, and then you use your kind of intuition that what could be the minimum f value, minimum m magnetization configuration. First of all, this magnetization configuration should be flat. So you can just replace this mx by a flat value, flat profile. Then you ask what is the value of this flat profile, like this. So that's the idea. But that can be done very easily just by considering that once it is flat, then you can say that okay, everywhere it has a mean value, and there is some small fluctuation, and just put that thing, compute it, and then self-consistently find out what is the mean value. Is this clear? Okay. So let's H is, I just write a sigma I equal to some mean value plus delta sigma I, and if you put that thing, then you can write this thing as, I don't want to do any mistake, I just write it directly from here, is 1 by half n j z m square. Let's not do write m naught, otherwise I will have to write m naught everywhere. And then you'll have H plus j z m and sigma I. Okay, and now this is an effective mean field Hamiltonian. Now you can do the partition function and compute everything, and you can show that once you compute the partition function and then write down the free energy, here will be a function of m, h, and temperature, right? I write this thing explicitly, and you can write it explicitly. Let me write it, m square by 2 theta. Let me write it first, and then I'll write what it is, plus h by theta. Now I just have used some dimensionless non-dimensional variables. So this is zj, theta is kbt by zj, and f, let's call it f, m h theta. F m h theta is the free energy per particle, is f by n zj. Zj is the energy, so everything is dimensionless. This quantity is also dimensionless. Everything is dimensionless. Okay, this is a simple calculation. You just write. So now you have to analyze this function. So how do we find out the equation of state? You have to minimize the free energy, and you have to minimize the free energy given theta. Theta is the temperature at different temperature, and h you just minimize and find out the equation of state. And from this you will find that. So I'll just discuss the h equal to 0 case, and then a non-zero case you can find. So if you find out del f del m equal to 0, to find out this will give you a solution m as a function of m h theta. You see that m is given by tan hyperbolic something, mh plus m plus h by theta. Okay. So let's just consider the h equal to 0 case. So this is m equal to tan hyperbolic m by theta, and we have to find out the solution for a given theta. You see that if you plot, you have done this thing many times. So right hand side I plot as a function of m, and the left hand side is just the line like this. You see that for theta greater than 1, so here there is a theta c which is 1. So for theta greater than 1, you see that the function behaves like this. So there is only one solution, okay? But for theta less than theta c, you will see that the function will have two solutions. This one, and this one. Should be symmetric, of course. Now which one to choose? So you have to find out, so these things should correspond to the minima of the free energy. So at h equal to 0, you just plot f m 0 theta as a function of m. You see that for theta greater than theta c, which is 1, the function near 0 is like this. There is only one minima, which is m equal to 0. That's what we found. But as theta is less than theta c, you see that there are two minima and one maxima. So this gives you minima, maxima, and these two are minima. And you see that you start getting both solution, and both are valid, and that's why you get coexistence. Okay. So this Then you can generalize this. You can actually try to find out how does this solution change. So let's say this is theta greater than theta c. Now let's say just theta just less than theta c, very close to theta c, but from below. How does this solution behave? You can just find out what is the solution, and that you can show that this m naught will go as square root 3 theta c minus theta by half, power half. So this actually gives rise to an expression. You see that there is a power law behavior. It goes to 0 as a power law. Similar power law you can see in the liquid gas transition when you approach T to Tc from below. What is the difference between the liquid and gas fraction, the density? That thing goes to 0 by as T minus Tc power half. You get the same exponent. And then there are other exponents also, which I do not have time to go. But yeah, so this is the idea of phase transition. This much I can tell so that you can recall some of the stops that you have learned in phase transition. Okay, so I'll stop here. So any question?